In this lecture, we're going to talk about solubility and the factors that affect solubility. Solubility is a really important concept when we're talking about solutions because it describes the amount of solute that can be dissolved in a given volume of solvent at a given temperature. Now, solubility is highly temperature dependent. The rule of thumb is that as temperature goes up, the solubility of a given compound is also going to go up. You're going to be able to dissolve more of your solute in the solvent at higher temperatures. Now, solubility values vary by compound. Each compound has its own solubility value in a given solvent. And of course, it's very temperature dependent. So as an example, let's look at sodium acetate, which is a salt, versus silver acetate, which is another salt. So the only difference here is the cation. And you can see that the solubility values per 100 grams of water at 20 degrees Celsius are extremely different. Sodium acetate is highly soluble. You can dissolve 46.5 grams of it in 100 grams of water at 20 degrees Celsius. Compared with silver acetate, you can only dissolve 1 gram of it per 100 grams of water at 20 degrees Celsius. So this goes back to a concept from before, which is solubility rules of different salts. So we talked about how depending on what ions are in salts, they have different solubilities. And silver salts tend to be relatively insoluble, whereas sodium salts tend to be very soluble. And you really see that in action here in these two solubility values. So what governs solubility? Solubility, the extent of it, depends on the attractive forces that exist between solute particles and solvent particles. And here, like dissolves like is the mantra that governs solubility. It's literally as simple as that. When we say like dissolves like, we're talking about polarity. So what that means is that polar solutes are going to be apt to dissolve in polar solvents. Okay, so polar dissolves in polar. Polar solutes dissolve in polar solvents. For example, ethanol, okay, CH3CH2OH, dissolves in water very easily. Both of these compounds are polar. Both of them are capable of forming hydrogen bonds. Like dissolves like, ethanol will dissolve in water. Um, Also, we can say salts will dissolve in water. So another example here would be sodium chloride, we know is highly soluble in water. Sodium chloride is going to dissolve in water easily because it has positively and negatively charged ions. And water is very polar. So an ionic salt releases charged particles, ions, and those ions are going to be complexed by the very polar water molecules. We'll talk about that a little bit more in the future. So conversely, nonpolar solutes dissolve in nonpolar solvents. Let me give you an example of that. Hydrocarbons, for example, will dissolve in each other. So C5H12, this is pentane, will dissolve in hexane. Okay, you could say hexane will dissolve in pentane, either way. Both of these are nonpolar. They are going to be dissolving in each other because they're both, all they have is London dispersion forces at play. Now, if I tried to dissolve pentane in water, it wouldn't work, okay? I can't get those two to dissolve in each other. So we would have them be immiscible, okay? So let's say hexane, for example. So, but C6H14 is immiscible. Immiscible is an adjective that means you can't mix it. Immiscible with water. Because you have a nonpolar compound, hexane, you have a very polar liquid, water, you can't mix those two. When you try to mix them, they'll form a bilayer because they are not interested in each other at all, okay? Polar polar species are not interested in dissolving nonpolar species. This explains why when you try to mix oil and water, you get a bilayer, right? Those are immiscible. Oil and water are immiscible because oil is nonpolar, water, vinegar is water-based. So I'm thinking of salad dressing, but water or vinegar, either one, those are both water-based. They don't mix with oil because they're polar. All right, so I hope that makes sense. Let's talk a little bit about temperature. As I said a moment ago, solubility increases with temperature for a given compound. So the higher the temperature, the more soluble, the more of your solutes you're going to get to dissolve in a given volume of solvent. You can think about this. Is it easier to dissolve sugar in iced tea or in hot tea? Well, hot tea, of course, it's much easier to dissolve sugar in hot tea because the solubility of sucrose, of course, is going to increase at the higher temperature. In fact, it's very difficult to dissolve sugar in iced tea. And a lot of times you'll use a simple syrup rather than solid sugar because it's difficult to dissolve sugar in ice cold water. Okay, if we're thinking about gases, then in that case, we think about pressure, of course, and solubility increases with pressure. So if you have a gas at higher pressure over a liquid, you're going to be able to force more of that gas into the liquid to dissolve in the liquid. Okay, so for gases, solubility increases as pressure increases. So as temperature increases, solubility increases. And for a gas, as pressure increases, solubility increases. So what governs solubility? Okay, we have to think about the process of solvation. And when I say solvation, I mean the dissolution of solute in solvent. How does a solute become solvated? By the solvent particles. Well, that process can be endothermic. That means that it requires energy input, but it can also be exothermic, meaning that it releases energy. In order to tell which one it is, you need to consider two different factors and kind of add them together. So the first factor is how much energy is required to break the bonds or to break the intermolecular forces that hold the particles together in the solid. The second factor that you need to consider is how much energy is either released or absorbed via solute-solvent interactions. So the first factor here is always going to be endothermic because it requires energy input to break bonds, okay? It requires energy input to break intermolecular forces. So this first factor here is going to be always endothermic because it's energy that's required. The second factor, however, can be exothermic or endothermic, depending on what kind of solute-solvent interactions you have. So let me give you an example. Let's take the salt strontium chloride, and I want to think about dissolving strontium chloride in water. So this is the strontium chloride dissolving in water. So let's consider factor number one, which was the energy required to break the bonds in strontium chloride. So we start out with strontium chloride solid, and we want to rip the strontium and chloride ions apart from each other to make gaseous ions. This might ring a bell to you. This process is the opposite of what we called the lattice energy. So remember, the lattice energy is the energy that is released when you pack gaseous ions together to form a crystalline solid. This is literally the opposite of that. How much energy does it take to rip an ionic solid apart, to rip a crystal lattice apart to get gaseous ions? Quite a lot, as it turns out. The delta H for this is above 2,000 kilojoules, so 2,114 kilojoules. It takes a lot of energy to break those ionic bonds. Now, the second factor is how much energy is released or absorbed via solute-solvent interactions. So here we want to think about what happens when we take those gaseous ions and hydrate them. So all we're doing here is hydrating the gaseous ions. And what that looks at is how much energy is going to be released or absorbed when the water molecules start complexing those ions, the strontium and chloride ions. That is a very exothermic process. So I'm going to have more than 2,161 kilojoules of energy released. So this process is known as the heat of hydration. So up here, this process was the opposite of the lattice energy, the reverse of the lattice energy. And the second process here is the delta H associated with it would be the heat of hydration, because we're literally hydrating those ions. All right, now I want to take those two reactions and add them together. Notice that I have lots of things that are the same on both sides, right? I have the strontium gaseous ions. I can cancel those out because they're the same on both sides. I have the two chloride ions, and I can cancel those out because they're the same on the opposite sides. So when I add those together, I'm left with strontium chloride solid breaking apart into aqueous ions. So this is literally the dissolution of strontium chloride in water. And to figure out the delta H, I have to add those two other delta H's together. So 2,114 kilojoules plus negative 2,161 kilojoules. So the delta H of this process is minus 47 kilojoules. And it just so happens that this is an exothermic process. So this would be the heat that is released when strontium chloride dissolves in water. It is also known as the heat of solution. Okay, heat of solution. So the heat of solution is the enthalpy change associated with dissolving a salt in a solvent, in this case, water. All right, and you can see that the heat of solution is equal to the opposite of the lattice energy. So I'm going to call that delta HLE, lattice energy, but it's the opposite of the lattice energy, the reverse of it. So I'm going to put a negative sign there, plus the heat of hydration, as we just saw in that calculation.